Our next lecture begins with the last chapter of your textbook. So we're going to be talking about cosmology and particle physics. Now, cosmology is the study and the character and evolution of the universe. So basically, it's the study of the universe as a whole. Where did it come from? What are its current properties, and where is it going? What will the universe look like a billion years in the future, 10 billion years, 100 billion years, and so on. So to understand that, we rely on the topic of astronomy. Astronomy is a subfield of physics. It is its own major and its own degree. I have a degree in astronomy. The important part to note is, though, is astronomy is really physics in space. So this is completely apropos to a physics textbook. Now there are, in the observable universe, about 100 billion galaxies. Now we have not observed them all because there are just so many, and also we have a limited number of telescopes scanning the sky. But this is done, an estimate is done basically taking a very detailed sample of a very small part of the sky and extrapolating outward. It's very much like counting how many jelly beans are in a jar. Count a small area and then extrapolate. And in each galaxy, you can have upwards of 100 billion stars. Some galaxies have fewer, some galaxies can have as many as several trillion stars. So there are a ridiculous number of stars in our universe. To measure distances in our universe, to talk about the scale of our universe, the units that we currently use, miles for English system, meters for the SI system, they're far too small to really give a good sense of how big things can get. So we use the actual property of light, the light travel time, the distance it takes light to go between distances. Now the speed of light is ridiculously fast. It can go from the Earth to the Sun in about 8.3 minutes. It takes about a second to go to the Moon. But over the distances of our galaxy, a light year, the distance the light travels in a year, is an appropriate distance to use when talking about distances between stars. Alternatively, light years are typically used in astronomy when dealing with astronomy magazines and popularized astronomy books. But astronomers themselves typically use what are called parsecs. A parsec is a similar unit, it's defined differently, but it's about, one parsec is about 3.26 light years. So it's a little bit bigger than a light year, but they're on the same scale. So distances in the universe are measured using light years. Our Milky Way Galaxy, our galaxy contains about 100 billion stars or more. The estimates go all the way up to 400 billion stars. And the galaxy itself looks like a pinwheel. It's a spiral, like a thin, flattened disk of stars, and our sun is orbiting in that disk, about 30,000 light years from the center of our galaxy. The galaxy itself is about 100,000 light years end to end. So that's the diameter of our galaxy. So it takes light 100,000 years to go from one end of our galaxy to the other. And that's just our galaxy. Our nearest large galactic neighbor, a galaxy of similar stature to our own Milky Way, is the Andromeda Galaxy. The Andromeda Galaxy is over 2 million light years away. That means if there were people or aliens in the Andromeda Galaxy and they had a powerful enough telescope, which won't exist, but let's pretend it does, and they could look at the Earth from that distance and see the Earth, right now they'd be seeing the Earth as it was 2 million years ago. Because the light coming off the Earth today will take another 2 million years to reach the Andromeda Galaxy. So when we look at the Andromeda Galaxy here on Earth, we see the Andromeda Galaxy as it was 2 million years ago. That's really an interesting result of astronomy, is the speed of light being finite means that the further away an object is, the further back in time we're looking at that object. So we're seeing the moon as it was about 1 light second ago. We're seeing the sun as it was about 8.5 light minutes ago. We're seeing the Andromeda Galaxy as it was 2 million years ago. And the further away, we're seeing objects dating back to just a few 100 million years after the start of our universe and what is called the Big Bang. So we can actually, as astronomers, see the early universe. We can't see what the Milky Way looked like 10 billion years ago, but we can see what distant galaxies looked like 10 billion years ago. And it gives us a sense of what our part of the universe would have looked like 10 billion years ago. It's a very, very interesting result. The analogy would be, and not realistic analogy, imagine a biologist studying animals. You're out in the wilderness, and the further away you look, the further back in time you're looking. So all the animals surrounding you are animals that exist today. But if you look 100 meters away, suddenly you see saber-toothed tiger and woolly mammoth. You look 1,000 meters away, you can see dinosaurs. So it's an interesting result that allows us to study the early universe from Earth without having, of course, been at the universe when it was very, very, very young. In the 1920s, astronomer Edwin Hubble took a telescope and looked at the distances and recession velocities of galaxies that he could see in the night sky. So using the Doppler shift, which we learned about when we talked about sound last semester, since light also travels as a wave, you can use the frequency shift of light at very specific wavelengths, like those given off by hydrogen gas, to measure how fast a galaxy is moving towards you or away from you. Now, the Andromeda Galaxy and a couple other nearby galaxies have some small local motion towards us. But the further away we get from the Milky Way, the faster galaxies are moving away from us. So the universe is expanding. So it's not like an explosion where the pieces of the universe are just moving away from a central location. But think of it rather as the fabric of the universe itself expanding. So think of the classroom that you might be sitting in this semester in one of your classes. Now imagine that the floor is made of a stretchy rubber material. Without moving at all, standing in the same location, if the floor just stretched out in all directions, people would move away from one another as they got stretched away, as the floor expanded between them and their neighbors. The further away you are from someone, the more floor between you and them, and therefore the more stretching you experience. So Hubble concluded that this strongly suggests that the universe was smaller in the past. So if there's expansion going on now, if you run the film backwards, that means the universe must have been smaller in the past. Keep on moving it backwards, and you find out that about 13.8 billion years ago, the universe would have been basically a point. Now, Hubble's discovery, I'll show a graph up here on the right. Hubble's discovery shows that the recession velocity of a galaxy, as a function of its distance, has a slope that we have called h0, which is the Hubble constant. The Hubble constant, named after Hubble who discovered it, is current measurements put it at around 72 kilometers per second per megaparsec. That means for every million parsecs away a galaxy is, it's receding from us at an average of about 72 kilometers per second. 2 megaparsecs away, it's 144 kilometers per second. 3 megaparsecs away, it's 216 kilometers per second, and so on. You just continue to get faster and faster the further away an object is moving. Now, this Big Bang theory was actually, the name was kind of set up as an insult. Before this, it was thought the universe was constant, that it existed basically forever, unchanging, not expanding, not contracting. So Hubble's discovery was a shock to cosmology. And some cosmologists and some people in the press sort of dismissed this idea. I can't believe that you think the universe came about from some sort of Big Bang. That's just silly. Well, that's the name that stuck. And it's the current theory that has the most evidence supporting it in cosmology. So, it's believed that about 13.8 billion years ago, the universe itself was smaller than the nucleus of an atom, and very rapidly came into existence, expanded and cooled into the universe as we see it today. Now, if that's true, there should be some observational evidence to support it, and we will talk about one of those big pieces of observational evidence, the cosmic microwave background. One of the largest pieces of supporting evidence for the Big Bang theory is the discovery and analysis of what's called the cosmic microwave background, or the CMB. Now, if the universe formed out of an explosion, a Big Bang, it would have been much denser and much hotter than the universe is today. As it expanded and cooled, it would have gone through many different stages until eventually the universe would have cooled enough that atoms would be able to be formed and the universe would become transparent. So the early universe was like the inside of a star, or even more dense than that. Light wouldn't travel very far before bouncing off charged particles like electrons or protons floating about, and the universe would have been opaque, the entire universe. As it expanded and cooled, electrons could then attach themselves to protons and form neutral atoms. Those neutral atoms then would allow light to pass through. So the epoch of when the universe became transparent is called recombination. That epoch would be notified, we'd be able to see back to it to when the universe was much hotter, around the 10,000 or 11,000 Kelvin or so. Now that light, when the universe is 10 or 11,000 Kelvin hot, is flying through the distant universe to reach us. Remember, when we look far back into the distant universe, we're looking far back in time. If you look way to the visible boundaries of the universe that we see today, we see this cosmic microwave background. It's cosmic, meaning it's everywhere. It's a background, it's in all locations. And microwave because the light, when the universe stretched, the wavelengths of light, which would have been visible light, were stretched to longer wavelengths and are now in the microwave region. So we can see this cosmic microwave background in an image shown here on the right. That image of the cosmic microwave background is the entire universe in all directions. So think of it like a map of the sky in all directions. And you can see that there are very, very, very small perturbations or fluctuations in the cosmic microwave background. Those tiny differences in temperature, and they are tiny, millions, thousands to millions of a Kelvin difference, those differences lead to the formation of what's called large-scale structure in our universe. Those slight hot bits in the cosmic microwave background would eventually form into the hot and cool bits would eventually form into galaxy clusters and large-scale structure in the universe. So the cosmic microwave background was predicted to exist before it was discovered, and it was discovered by accident by two Bell Labs scientists studying microwave transmissions of basically telephone signals for Bell Labs, which became AT&T. So the cosmic microwave background is a huge bit of supporting evidence for this Big Bang theory. Additionally, one thing astronomers and physicists could not explain is the universe today being matter dominated. What do I mean by that? Well, the matter that you and I are made up of and everything around us is regular matter, not antimatter. Well, if the universe was pure energy to begin with and formed matter, it should have formed matter and antimatter equally, which would have then come back and destroyed one another. So why is there matter in the universe, a lot of matter and not a lot of antimatter, right? Mars is not made of antimatter. We've landed probes on it. If Mars were made of antimatter, those probes would have basically blown up. We know other stars aren't made of antimatter because of the way they interact with other objects in our galaxy. So our universe is matter dominated. So during the Big Bang, for every billion antimatter particles that were created out of the energy soup of the early Big Bang, about 1,000,000,001 particles of matter were created. Those billion particles of matter and antimatter annihilated, but leaving behind that one additional particle of matter, that those build up over time, giving us the matter that we see in the universe today. Now, the early universe, the physics we have today can't explain the early universe well. This is why we're trying to find those grand unified theories and the theory of everything that we talked about in earlier lectures. Right now, the universe, at its current temperature and its current state, and its current temperature is about 2.7 Kelvin above absolute zero. The universe, there are four fundamental forces in the universe: the nuclear strong force, the nuclear weak force, the electromagnetic force, and gravity. As you go back in time, the universe gets smaller and hotter. Eventually, the universe is hot enough that the electromagnetic force and the weak force are actually act as one. We call that the electroweak force. Go back farther in time, the nuclear strong force comes in, and that was what we call the grand unified theory, combining the nuclear strong force, the nuclear weak force, and the electromagnetic force. So if we want to understand the universe at this very early stage in the universe's existence, we need a grand unified theory, and we don't currently have one. We're working on it, but we don't currently have one. And then if we want to know how the universe behaved even earlier in its existence, when it was so dense and so hot that all forces acted as one, where gravity was thrown into the mix, this theory of everything, we need that theory of everything to be able to explain the universe at its very earliest stages. We don't have the physics today to explain why the Big Bang occurred. I believe it was famous physicist Stephen Hawking, who passed away just a few years ago, who stated once we discover the theory of everything, he would like to see the equations just like, oh, of course we have a universe, because these equations show what would happen in this situation. Or of course the universe is matter dominated, because this asymmetry between matter and antimatter formation is explained through these equations. So the graph shown here shows basically the history of the universe, from its very earliest stages down at the bottom to where it currently is. We're in what's called the stellariferous era of the universe, where stars are forming continuously, but eventually stars will run out. So the long-term fate of the universe is the universe right now, we believe, will continue to expand, continue to accelerate. If protons do have a half-life and decay, eventually matter will decay very slowly with time, and the very end of the universe in trillions of years in the future, a googolplex years in the future, right? We're talking about the universe being basically just this soup of photons, neutrinos, electrons, and positrons. So not a very exciting end to the universe, which started off with a bang, but ends definitely on a whimper.